Hello everyone, I am Muskan from Chemistry Honors. My roll number is 21. Today I am going to continue the reading of chapter P block. So, properties of dioxygen. Dioxygen is a colorless and odorless gas. Its solubility in water is to extent of 3.08 centimeter cube in 100 centimeter cube water at 293 Kelvin, which is just sufficient for the vital support of marine and aquatic life. It liquefies at 90 Kelvin and freezes at 55 Kelvin. It has three stable isotopes 16O, 17O, and 18O. Molecular oxygen O2 is unique in being paramagnetic in spite of having even number of electrons. Dioxygen directly react with nearly all metal and non-metal except some metals and some noble gases. Its combination with other elements is often strongly exothermic, which helps in sustaining the reaction. However, to initiate the reaction, some external heating is required as bond dissociation enthalpy of oxygen-oxygen double bond is high. Uses. In addition to its importance in normal respiration and combustion processes, oxygen is used in oxoacetylene welding, in manufacture of many metals. Simple oxides. A binary compound of oxygen with another element is called oxide. As already stated, oxygen reacts with most of the elements of the periodic table to form oxides. In many cases, one element forms two or more oxides. The oxides vary widely in their nature and properties. Oxides can be simple or mixed. Simple oxides can be classified on the basis of their acidic, basic, or amphoteric character. An oxide that combine with water to give an acid is termed acidic oxide. For example, SO2 combines with water to give H2SO3, an acid. As a general rule, only non-metal oxides are acidic, but oxides of some metal in high oxidation state also have acidic character. The oxide which give a base with water are known as basic oxides. In general, metallic oxides are basic. Some metallic oxides exhibit a dual behavior. They show characteristics of both acidic as well as basic oxides. Such oxides are known as amphoteric oxides. They react with acid as well as alkalis. There are some oxides which are neither acidic nor basic. Such oxides are known as neutral oxides. Ozone. Ozone is an allotropic form of oxygen. It is too reactive to remain for long in the atmosphere at sea level. At the height of about 20 kilometers, it is formed from atmospheric oxygen in the presence of sunlight. This ozone layer protects Earth's surface from the excessive concentration of ultraviolet radiations. Preparation. When a slow, dry stream of oxygen is passed through a silent electrical discharge, conversion of oxygen to ozone 10% occurs. The product is known as ozonized oxygen. Since the formation of ozone from oxygen is an endothermic process, it is necessary to use a silent electrical discharge in its preparation to prevent its decomposition. In concentrations of ozone greater than 10% are required, a battery of ozonizers can be used and pure ozone can be condensed in a vessel surrounded by liquid oxygen. Properties. Pure ozone is a pale blue gas, dark blue liquid, and violet black solid. Ozone has a characteristic smell and in small concentrations it is harmless. However, if the concentration rises above 100 parts per million, breathing becomes uncomfortable, resulting in headache and nausea. Ozone is thermodynamically unstable with respect to oxygen since its decomposition into oxygen results in the liberation of heat. and increase in entropy. These two effects reinforce each other, resulting in negative Gibbs energy change for its conversion into oxygen. It is not really surprising, therefore, high concentration of ozone can be dangerously explosive. Due to the ease with which it liberates atoms of nascent oxygen, it acts as powerful oxidizing agent. It oxides lead sulfide to lead sulfate and iodide ions to iodine. When ozone reacts with an excess of potassium iodide solution buffered with borate buffer, iodine is liberated, which can be titrated against a standard solution of sodium thiosulfate. This is a quantitative method of estimating O3 gas. Experiments have shown that nitrogen oxides combine very rapidly with ozone, and there is thus the possibility that nitrogen oxides emitted from the exhaust system of supersonic jet aeroplane might be slowly depleting the concentration of the ozone layer in upper atmosphere. Another threat to this ozone layer is probably posed by use of freons, which are used in aerosol sprays and as refrigerants. The two oxygen-oxygen bond length in ozone molecule are identical, and molecule is angular as expected with a bond angle of about 117 degree. It is a resonance hybrid of two main forms. It is used as a germicide, disinfectant, and for sterilizing water. Sulfur allotropic forms. Sulfur forms numerous allotropes, of which the yellow rhombic, alpha sulfur, and monoclinic beta sulfur forms are the most important. The stable form at room temperature is rhombic sulfur, which transforms to monoclinic sulfur when heated above 369 Kelvin. Rhombic sulfur, alpha sulfur. This allotrope is yellow in color, melting point 385.8 Kelvin and specific gravity. Rhombic sulfur crystals are formed on evaporating the solution of roll sulfur in CS2. It is insoluble in water but dissolves to some extent in benzene, alcohol and ether. It is readily soluble in CS2. Monoclinic sulfur, beta sulfur. Its melting point is 393 Kelvin and specific gravity is 1.98. It is soluble in CS2. This form of sulfur is prepared by melting rhombic sulfur in a dish and cooling till crust is formed. Two holes are made in the crust and the remaining liquid poured out. On removing the crust, colorless needle-shaped crystals of beta sulfur are formed. It is stable above 369 Kelvin and transforms into alpha sulfur below it. Conversely, alpha sulfur is stable below 369 Kelvin and transformed into beta sulfur above this. At 369 Kelvin, both the forms are stable. This temperature is called transition temperature. Both rhombic and monoclinic sulfur have S8 molecules. These molecules are packed to give different crystal structures. The S8 ring in both the form is puckered and has a crown shape. Several other modifications of sulfur containing 6 to 20 sulfur atoms per ring have been synthesized in the last 2 decades in cyclo-S6. The ring adopts the chair form and the molecular dimensions are as shown in figure. At elevated temperatures, S2 is the dominant species and is paramagnetic like O2. Sulfur dioxide. Sulfur dioxide is formed together with a little sulfur trioxide when sulfur is burnt in air or oxygen. In the laboratory, it is readily generated by treating a sulfide with dilute sulfuric acid. Industrially, it is produced as a byproduct of roasting of sulfide ores. The gas, after drying, is liquefied under pressure and stored in steel cylinders. Property: sulfur dioxide is a colorless gas with pungent smell and is highly soluble in water. It liquefies at room temperature under a pressure of 2 atmospheres and boils at 263 Kelvin. Sulfur dioxide, when passed through water, forms a solution of sulfurous acid. It readily reacts with sodium hydroxide solution, forming sodium sulfite, which then reacts with more sulfur dioxide to form sodium hydrogen sulfide. In its reaction with water and alkalis, the behavior of sulfur dioxide is very similar to that of carbon dioxide. Sulfur dioxide reacts with chlorine in the presence of charcoal to give sulfuryl chloride. It is oxidized to sulfur trioxide by oxygen in the presence of vanadium oxide catalyst. When moist sulfur dioxide behave as a reducing agent. For example, it converts iron thrice ions to iron twice ions and decolorizes acidified potassium permanganate 7 solution. The latter reaction is a convenient test for the gas. Sulfur dioxide is used in refining petroleum and sugar, in bleaching wool and silk, and as an anti-clone, disinfectant, and preservative. Oxoacids of sulfur. Sulfur forms a number of oxoacids such as H2SO3, H2SO3, H2S2O4, H2S2O5, etc. Some of these acids are unstable and cannot be isolated. These are known in aqueous solution or in the form of their salts. Structure of some important oxoacids. Sulfuric acid manufacture. Sulfuric acid is one of the most important industrial chemical worldwide. Sulfuric acid is manufactured by the contact process, which involves three steps: burning of sulfur or sulfide ores in air to generate SO2, conversion of SO2 to SO3 by reaction with oxygen in the presence of a catalyst, and absorption of SO3 in H2SO4 to give oleum. Flow diagram for manufacture of sulfuric acid is shown. The SO2 produced is purified by removing dust and other impurities such as arsenic compound. The key step in manufacture of H2SO4 in the catalyst oxidation of SO2 with O2 to give SO3 in the presence of V2O5. The reaction is exothermic, reversible, and the forward reaction leads to a decrease in volume. Therefore, low temperature and high pressure are favorable conditions for maximum yield, but the temperature should not be very low, otherwise rate of reaction will become slow. Flow diagram for manufacture of sulfuric acid. SO3 gas from the catalyst converter is absorbed in concentrated H2SO4 to produce oleum. Dilution of oleum with water gives H2SO4 of desired concentration. In the industry, two steps are carried out simultaneously to make the process a continuous one and also to reduce the cost. The sulfuric acid obtained by contact process is 96 to 98% pure properties. Sulfuric acid is a colorless, dense, oily liquid with specific gravity of 1.84 at 298 Kelvin. The acid freezes at 283 Kelvin and boils at 611 Kelvin. It dissolves in water with evolution of a large quantity of heat. Hence, care must be taken while preparing sulfuric acid solution from concentrated sulfuric acid. The concentrated acid must be added slowly into water with constant stirring. The chemical reaction of sulfuric acid are as a result of following characteristic: low volatility, strong acidic character, strong affinity for water, and ability to act as an oxidizing agent. The larger value of Ka means that H2SO4 is dissociated into H positive and HSO4 negative. Greater the value of dissociation constant Ka, the stronger is the acid. The acid form two series of salt, normal sulfates and acid sulfates. Sulfuric acid became, because of its low volatility, can be used to manufacture more volatile acids from their corresponding salts. Concentrated sulfuric acid is a strong dehydrating agent. Many wet gases can be dried by passing them through sulfuric acid. Provided the gases do not react with the acid, sulfuric acid removes water from organic compounds. It is evident by its jarring action on carbohydrates. Hot concentrated sulfuric acid is a moderately strong oxidizing agent. In this respect, it is intermediate between phosphoric and nitric acid. Both metal and non-metal are oxidized by concentrated sulfuric acid, which is reduced to SO2. Sulfuric acid is very important industrial chemical. Group 17 elements. Fluorine, chlorine, bromine, iodine, and astatine are members of group 17. These are collectively known as halogens. The halogens are highly reactive non-metallic elements. Like group 1 and 2, elements of group 17 show great similarity amongst themselves. That much similarity is not found in the elements of other group of the periodic table. Also, there is a regular gradation in their physical and chemical properties. Acetine is radioactive element. Occurrence. Fluorine and chlorine are fairly abundant while bromine and iodine less so. Fluorine is present mainly as insoluble fluorides, and small quantities are present in soil, river water, plant, and bones and teeth of animal. Seawater contain chlorides, bromides, and iodides of sodium, potassium, magnesium, calcium, but is mainly sodium chloride solution. The deposits of dried up seas contain these compounds. Certain forms of marine life contain iodine in their system. Various seaweed the trend of some of the atomic physical and chemical properties. Electronic configuration. All these elements have 7 electrons in their outermost shell, Ns2 and p5, which is 1 electron short of the next noble gas. Atomic and ionic radii. Halogens have the smallest atomic radii in their respective periods due to maximum effective nuclear charge. The atomic radius of fluorine, like the other element of second period, is extremely small. Atomic and ionic radii increases from fluorine to iodine due to increasing number of quantum shell. Ionization enthalpy. They have little tendency to lose electron, thus they have very high ionization enthalpy. Due to increase in atomic size, ionization enthalpy decreases down the group. Halogens have maximum negative electron gain enthalpy in the corresponding period. This is due to the fact that the atom of these elements have only one electron less than stable noble gas configuration. Electron gain enthalpy of the element of the group become less negative down the group. However, the negative electron gain enthalpy of fluorine is less than that of chlorine. It is due to small size of fluorine atom. As a result, are strong interelectronic repulsions in the relatively small 2p orbital of fluorine, and thus incoming electron does not experience much attraction electronegativity. They have high electronegativity. The electronegativity decreases down the group. Fluorine is the most electronegative element in the periodic table. Physical properties. Halogen display smooth variations in their physical properties. Fluorine and chlorine are gases, bromine is a liquid, and iodine is a solid. Their melting and boiling points steadily increase with atomic number. All halogens are colored. This is due to absorption of radiation in visible region, which result in the excitation of outer electron to higher energy level. By absorbing different quanta of radiation, they display different colors. For example, F2 has yellow, Cl2 greenish yellow, Br2 red, and I2 violet color. Fluorine and chlorine reacts with water. Bromine and iodine are only sparingly soluble in water but are soluble in various organic solvents such as chloroform, carbon tetrachloride, carbon disulfide, and hydrocarbons to give colored solutions. One curious anomaly we notice is the smaller enthalpy of dissociation of fluorine compared to that of chlorine, whereas halogen-halogen bond dissociation enthalpy from chlorine onwards show the expected trend. Chlorine-chlorine bond is greater than bromine-bromine greater than iodine-iodine. A reason for this anomaly is relatively larger electron-electron repulsion among the lone pair in fluorine molecules, where they are much closer to each other than in case of chlorine. Chemical properties, oxidation state and trends in chemical reactivity. All the halogens exhibit -1 oxidation state. However, chlorine, bromine, and iodine exhibit +1, +3, +5, +7 oxidation state also explained. The higher oxidation state of chlorine, bromine, and iodine are realized mainly when the halogens are in combination with the small and highly electronegative fluorine and oxygen atom. The oxidation state of +4 and +6 occur in oxides and oxoacids of chlorine and bromine. The fluorine atom has no d orbital in its valence shell and therefore cannot expand its octet. Being the most electronegative, it exhibits only -1 oxidation state. All the halogens are highly reactive. They react with metal and non-metal to form halides. The reactivity of the halogens decreases down the group. The ready acceptance of an electron is the reason for the strong oxidizing nature of halogens. F2 is the strongest oxidizing halogen and it oxidizes other halide ion in solution or even in the solid phase. In general, a halogen oxidizes halide ion of higher atomic number, decreasing oxidizing ability of halogen in aqueous solution down the group is evident from their standard electrode potentials, which are dependent on the parameters indicated below. The relative oxidizing power of halogens can further be illustrated by the reaction with water. Fluorine oxidizes water to oxygen, whereas chlorine and bromine react with water to form corresponding hydrohalic and hydrocohalous acid. The reaction of iodine with water is non-spontaneous. In fact, iodine can be oxidized by oxygen in acidic medium, just the reverse of the reaction observed with fluorine. Anomalous behavior of fluorine. Like other elements of P block present in second period of periodic table, fluorine is anomalous in many properties. For example, ionization enthalpy, electronegativity, enthalpy of bond dissociation, and electrode potential are all higher for fluorine than expected from the trend set by other halogens. Also, ionic and covalent radii, melting point and boiling point, and electron gain enthalpy are quite lower than expected. The anomalous behavior of fluorine is due to its small size, highest electronegativity, low fluorine-fluorine bond dissociation enthalpy, and low availability of d orbital in valence shell. Most of the reactions of fluorine are exothermic. It forms only one oxoacid while other halogens form a number of oxoacids. Hydrogen fluoride is a liquid due to strong hydrogen bonding. Other hydrogen halides are gases. Reactivity towards hydrogen. They all react with hydrogen to give hydrogen halide, but affinity for hydrogen decreases from fluorine to iodine. They dissolve in water to form hydrohalic acids. Some of the property of hydrogen halide is given. The acidic strength of these acids varies in order: HF, HCl, HBr, HI. HI is the greatest, and the stability of these halides decreases down the group due to decrease in bond dissociation enthalpy in the order. Hydrogen fluoride the highest and decreased by HCl, HBr, HI. Reactivity towards oxygen. Halogen form many oxide with oxygen, but most of them are unstable. Fluorine form two oxide OF2 and O2F2. However, only OF2 is thermally stable at 298 Kelvin. These oxides are essentially oxygen fluoride because of the higher electronegativity of fluorine than oxygen. Both are strong fluorinating agents. O2F2 oxidizes plutonium to PuF6, and the reaction is used in removing plutonium from spent nuclear fuel. Chlorine, bromine, and iodine form oxide in which the oxidation state of these halogens ranges from +1 to +7. A combination of kinetic and thermodynamic factors led to the generally decreasing order of stability of oxides formed by halogens. The greatest is iodine and decreases by chlorine and bromine. The higher oxide of halogen tend to be more stable than the lower one. Chlorine oxide Cl2O, ClO2, Cl2O6, Cl2O7 are highly reactive oxidizing agents and tend to explode. ClO2 is used as a bleaching agent for paper pulp and textile in water treatment. The bromine oxides Br2O and BrO2, BrO3 are least stable halogen oxides and exist only at low temperature. They are very powerful oxidizing agent. Oxide ion I2O4, I2O5, I2O7 are insoluble solids and decomposes on heating. I2O5 is a very good oxidizing agent and is used in the estimation of carbon monoxide. Reactivity towards metals. Halogen react with metal to form metal halides. The ionic character of halide decreases in the order Mf, McL, Mbr, Mi, where M is a monovalent metal. If a metal exhibits more than one oxidation state, the halide in higher oxidation state will be more covalent than the one in lower oxidation state. Reactivity of halogen toward other halogens. Halogens combine among themselves to form a number of compounds known as interhalogen of the type X, X dash, X, X dash 3, X, X dash 5, X, X dash 7, where X is a large size halogen and X dash is smaller size halogen. Chlorine. Chlorine was discovered in 1774 by Schlegel by the action of HCl on MnO2. In 1810, Davy established its elementary nature and suggested the name chlorine on account of its color. Greek chloros is equal to greenish yellow. Preparation. It can be prepared by any of the following methods. First, by heating manganese dioxide with concentrated hydrochloric acid. However, a mixture of common salt and a concentrated H2SO4 is used in place of HCl. Second, by the action of HCl on potassium permanganate. Manufacture of chlorine. Deccan's process. By oxidation of hydrogen chloride gas by atmospheric oxygen in presence of copper chloride catalyst at 623 Kelvin. Electrolytic process. Chlorine is obtained by electrolysis of brine concentrated sodium chloride solution. Chlorine is liberated at anode. It is also obtained as a byproduct in many chemical industries. Properties. It is a greenish yellow gas with pungent and suffocating odor. It is about 2 to 5 times heavier than air. It can be liquefied easily into greenish yellow liquid which boils at 239 Kelvin. It is soluble in water. It has great affinity for hydrogen. It reacts with compound containing hydrogen to form HCl. With excess ammonia, chlorine gives nitrogen and ammonium chloride, whereas with excess chlorine, nitrogen trichloride is formed. With cold and dilute alkalis, chlorine produces a mixture of chloride and hypochlorite, but with hot and concentrated alkalis, it gives chloride and chlorate. With a dry slaked lime, it gives bleaching powder. The composition of bleaching powder is CaOCl2, CaCl2, CaOH2, 2H2O. Chlorine reacts with hydrocarbon and gives substitution product with saturated hydrocarbon and addition products with unsaturated hydrocarbons. Chlorine water on standing loses its yellow color due to the formation of HCl and HOCl. Hypochlorous acid so formed gives nascent oxygen which is responsible for oxidizing and bleaching properties of chlorine. It oxidizes ferrous to ferric, sulfite to sulfate, sulfur dioxide to sulfuric acid, and iodine to iodic acid. It is a powerful bleaching agent. Bleaching action is due to oxidation. Colored substance plus oxygen gives colorless substance. It bleaches vegetable or organic matter in presence of moisture. Bleaching effect of chlorine is permanent. Uses. It is used for bleaching wood pulp, bleaching cotton and textile, in extraction of gold and platinum, in manufacture of dyes, drugs, and organic compounds, in sterilizing drinking water, preparation of poisonous gases such as phosgene, tear gas, mustard gas. Hydrogen chloride (HCl). Glauber prepared this acid in 1648 by heating common salt with concentrated sulfuric acid. Davy in 1810 showed that it is a compound of hydrogen and chlorine. Preparation. In laboratory, it is prepared by heating sodium chloride with concentrated sulfuric acid. HCl gas can be dried by passing through concentrated sulfuric acid. Property. It is a colorless and pungent smelling gas. It is easily liquefied to a colorless liquid and freezes to a white crystalline solid. It is extremely soluble in water and ionizes as below. Its aqueous solution is called hydrochloric acid. High value of dissociation constant indicate that it is strong acid in water, react with ammonia and give white fume of NH4Cl. When 3 part of concentrated HCl and 1 part of concentrated HNO3 are mixed, aquaresia is formed, which is used for dissolving noble metals. Hydrochloric acid decomposes salts of weaker acid. It is used in manufacture of chlorine, for extracting glue from bones and purifying bone black in medicine and it as a laboratory reagent. Oxoacids of halogen. Due to high electronegativity and small size, fluorine forms only one oxoacid HOF, known as fluoric. Fluoric 1 acid or hypofluorous acid. The other halogen form several oxoacids. Most of them cannot be isolated in pure state. They are stable only in aqueous solution or in form of their salt. The oxoacid of halogen are given and their structures. Halic acid 1, halic 3 acid, halic 5 acid, halic 7 acid. Interhalogen compound. When two different halogens react with each other, interhalogen compounds are formed. They can be assigned a general composition as XX XX thrice, XX 5, XX 7, and X is halogen of larger size, and X dash of smaller size, and X is electropositive than X dash. As the ratio between radii of X and X dash increases, number of atoms per molecule also increases. Thus, iodine 7 fluoride should have maximum number of atoms as the ratio of radii between iodine and fluorine should be maximum. That is why its formula is IF7. Preparation. The interhalogen compound can be prepared by direct combination or by action of halogen on lower interhalogen compound. The product form depends upon some specific conditions. These are all covalent molecules and are diamagnetic in nature. They are volatile solid or liquid except CIF, which is a gas at 298 Kelvin. Their physical properties are intermediate between those of constituent halogens, except that their melting point and boiling point are a little higher than expected. Their chemical reactions can be compared with individual halogens. In general, interhalogen compounds are more reactive than halogens. This is because halogen dash bond in interhalogen is weaker than halogen halogen bond in halogens, except fluorine fluorine bond. All these undergo hydrolysis, giving halide ion derived from the smaller halogen and hypohalite. Their molecular structure are very interesting, which can be explained on the basis of VSEPR theory. Uses. These compounds can be used as non-aqueous solvent. Interhalogen compounds are very useful fluorinating agents. Group 18 element. Group 18 consists of 6 elements: helium, neon, argon, krypton, xenon, and radon. All these are gases and chemically unreactive. They form very few compounds. Because of this, they are termed noble gases. Occurrence. All noble gases except radon occur in the atmosphere. Their atmospheric abundance in dry air is 1% by volume, of which argon is the major constituent. Helium and sometimes neon are found in minerals of radioactive origin. The main commercial source of helium is a natural gas. Xenon and radon are the rarest element of group. Radon is obtained as a decay product of Ra. Important atomic and physical property of group 18 element along with their electronic configuration are given. Electronic configuration. All noble gases have general electronic configuration ns2np6 except helium, which has one s2. Many of the properties of noble gases, including their inactive nature, are ascribed to their closed shell structures. Ionization enthalpy. Due to stable electronic configuration, these gases exhibit very high ionization enthalpy. However, it decreases down the group with increase in atomic size. Atomic radii increases down the group with increase in atomic number. Electron gain enthalpy. Since noble gas have stable electronic configuration, they have no tendency to accept the electron and therefore have large positive value of electron gain enthalpy. Physical property. All the noble gases are monoatomic. They are colorless, odorless, tasteless. They are sparingly soluble in water. They have very low melting and boiling points because the only type of interatomic interaction in these elements is weak dispersion forces. Helium has lowest boiling point of any substance. It has as unusual property of diffusing through most commonly used laboratory materials such as rubber, glass, or plastic. Chemical properties. In general, noble gases are least reactive. Their inertness to chemical reactivity is attributed to following reasons. The noble gas except helium have completely filled ns2 and p6 electronic configuration in their valence shell. They have high ionization enthalpy and more positive electron gain enthalpy. The reactivity of noble gas has been investigated occasionally ever since their discovery, but all attempts to force them to react to form the compound were unsuccessful for quite few years. In March 1962, Neil Bartlett, then at the University of British Columbia, observed the reaction of noble gas. First, he prepared a red compound which is formulated as O2 positive PTF6 negative. He then realized that the first ionization enthalpy of molecular oxygen was almost identical with that of xenon. He made efforts to prepare the same type of compound with xenon and was successful in preparing another red color compound by mixing platinum fluoride and xenon. After this discovery, a number of xenon compounds, mainly with most electronegative elements like fluorine and oxygen, have been synthesized. The compounds of krypton are fewer, only the difluoride has been studied in detail. Compounds of radon have not been isolated but only identified by radiotracer technique. No true compound of arsenic, neon, or helium are yet known. Xenon fluoride compound. Xenon forms three binary fluoride XeF2, XeF4, XeF6 by direct reaction of element under appropriate experimental conditions. These are colorless crystalline solids and sublime readily at 298 Kelvin. They are powerful fluorinating agents. They are readily hydrolyzed even by traces of water. The structure of 3-xenon fluoride can be deduced from VSEPR, and these are known have linear and square planar structure respectively. XeF6 has 7 electron pair and would thus have a distorted octahedral structure as found experimentally in gas phase. Xenon-oxygen compound. Hydrolysis of XeF4 and XeF6 with water gives XeO3. Partial hydrolysis gives oxyfluorides. XeO3 is a colorless explosive solid and has a pyramidal molecular structure. XeOF4 is a colorless volatile liquid and has a square pyramidal molecular structure. Helium is a non-inflammable and light gas, and hence it is used in filling balloons with meteorological observations. Our chapter is completed. Thank you.